Good afternoon. My name is Glynis Ritchie and I am one of the project coordinators for the A Proctor Group. In today's webinar, we're going to discuss measures to simplify achieving good airtightness in modular and off-site construction applications. We'll be looking at the key design considerations involved in building regulation compliance, strategies to manage the movement of heat, air and moisture in the building envelope, and considering good design and installation practice for air and vapour control membranes. As usual, we'll be following up with a Q&A session, so if you have any questions, please feel free to type them into our comment box or email us at webinar@proctorgroup.com. Based on the principle of DFMA, Design for Manufacturing and Assembly, volumetric or modular construction involves the off-site production of modular units. Categorised as a modern method of construction, MMC, they are built to last and deliver an incredible range of different options that can be tailored to suit every requirement. A range of products include unique off-site solutions for the following sectors: private and social affordable housing, purpose-built student accommodation, self-build projects, hotels, education and office buildings, healthcare including hospitals, health centres and healthcare facilities. As with any type of construction, the basis of good design in modular construction comes from a good understanding of the building regulations themselves. Today we'll be focusing mainly on the documents relating to energy performance and condensation control. So this would be approved documents L and F in England and Wales, Technical Standards 3 and 6 in Scotland, Technical Booklets K and F in Northern Ireland, and Guidance Documents L and F in the Republic of Ireland. While the specific details in these documents might vary a little, the principles behind the guidance and the recommended approaches are broadly similar. The first thing we need to consider is the type of building fabric we're dealing with. Concrete, steel and timber-based buildings all respond differently to moisture and contain different amounts of construction moisture which must be allowed to dry out. For example, buildings with a lot of in-situ concrete can take several years to fully dry out. This excess moisture load must be accounted for at the design stage. Construction moisture can also come from the weather, and this must also be taken into account along with the weather conditions the building will be subjected to once completed. Being weather-tight earlier in the construction process and generally being composed of drier materials, off-site construction has an important advantage hydrothermally. By reducing the initial moisture loading on the building fabric, the design can be more precisely tailored to manage moisture associated with the occupants of the building and the uses the building will be put to, leading in turn to a more efficient fabric envelope and building system. The influences of these three aspects can then be assessed in terms of heat, air and moisture movement within the building. This takes into account the heating of the building, as well as the air leakage effects and response to the building fabric to the absorption and desorption of moisture. Factors such as the position and performance of the fabric insulation can also be considered. To ensure our design adequately manages these complex interactions, we undertake a hydrothermal analysis of the building fabric using a software called WUFI. This breaks the building elements into individual layers and calculates the temperatures, moisture flow and degree of water storage at any point in the building fabric we choose to assess. Historically, a process known as the Glaser method was used to assess this. However, this method makes a few assumptions that limits its accuracy. In contrast, WUFI allows us to account for the variable external influences of weather conditions, along with the effects of the fabric capacity to store and release moisture. We can also look at how these factors interact over longer periods of time. The steady state analysis used in the Glaser method, while useful, does not always provide a sufficiently detailed picture of the long-term performance of the structure. This more detailed analysis can allow us to consider solutions that may not appear acceptable when assessed under the Glaser method. In our example here, the internal vapour control layer can be removed altogether without creating a condensation risk. This is made possible by the use of an external vapour-permeable air barrier membrane. Our wrap-tight membrane self-adheres to the external face of the sheathing and provides a robust airtight layer without compromising moisture movement through the wall assembly. This allows vapour control to be assessed independently of the airtight envelope and optimised to suit the position and type of insulation and the anticipated moisture loadings. By removing the vapour control in favour of an external air leakage solution, we achieve a few things. Firstly, we remove the associated material and installation costs, but more importantly, we remove the need to seal all the surface penetrations, meaning we have a more reliable air barrier and can reduce the air leakage rates used at the design stage. Reducing the air leakage from 3 meters cubed meter square per hour down to 1 can have a significant positive impact on the energy performance of the building, meaning we can reduce the insulation thickness required or the specification of the insulation boards themselves. This can offer designers more flexibility in insulation types used, for example as regards fire performance or increasing internal space available to occupants. We can, however, only take full advantage of this flexibility if we can depend on achieving the air leakage targets we use in the design process. As we can see here, if we keep the air barrier internal, that means a lot of tape and mastic required to seal all the switches, sockets, pipework and other services that modern buildings require. A lot of this sealing can be done off-site, but it still takes a lot of time to do correctly, and further care is required to ensure the seals are not broken or damaged during transportation and assembly. Even small punctures, broken or misaligned seals or loose tapes can significantly increase the air leakage rate when tested, leading to expensive and difficult remediation measures to meet regulation requirements. This process can be speeded up somewhat by proprietary seals and components, but this can increase costs and complicate supply chains. Using a fully adhered external barrier removes this problem completely, ensuring that the panels arrive in position perfectly sealed and the performance in practice match the design criteria without requiring any unusual measures or specialist products during the construction process. In modular systems, incorporating an external barrier is straightforward and brings several benefits over traditional mechanically fixed membranes. The membrane can be applied to the panels in any orientation, and being self-adhered requires no mechanical fixings. The adhesion reduces the potential for membrane damage both during the module assembly process and while in transit to site. The panels are then assembled and the joints taped using the same material in tape form, ensuring no adhesion issues or tape compatibility problems. Once the joints are taped, the panel assembly is resistant to air leakage, and any service installations such as wiring or pipework can be undertaken independently without risking damage to the airtight layer. These wall, roof and floor panels can then be assembled into modules, and the wrap-tight split liner tape used to complete the airtight seal between adjacent assemblies. This tape simplifies making such joints by splitting the release liner in half, allowing the two surfaces to be stuck independently, making the joint faster and more accurate. The completed modules can then be transported to site. During transportation, the self-adhered membrane ensures watertightness, protecting internal components and minimising on-site remediation work. The building can then be assembled on site and completed as normal. Many systems are accredited within BOPAS, Building Property Assurance Scheme, which offers assurance of structural integrity for modern methods of construction. Wrap-tight is currently included within 2 systems. As well as ensuring the integrity of the air barrier is maintained, the self-adhered wrap-tight membrane brings important benefits in terms of fire resistance. Since December 2018, membranes used in external walls over 18 metres in height have required a minimum fire rating of BS3D0. While there are some materials with A1 or A2 ratings that can be used to provide weather protection, they typically don't offer sufficient vapour permeability to ensure a healthy building envelope is maintained by allowing construction moisture in particular to dry out. Class B membranes are far better in permeability terms and don't usually contribute enough calorific value to have a significant effect on the development of a fire. The BR 135 guidance document uses the following model to illustrate the development of a fire. A rapid fire spread occurs when an initial fire develops and flashes over, and is then spread to all areas simultaneously by the outer cladding layers. This then starts fires across all areas of the building. In cases of restricted fire spread, the initial fire develops and flashes over, but is then either contained or will ignite a single secondary fire directly adjacent. The fire will only develop further if this secondary fire also develops. This is a much slower process. Let us consider solely how the membrane in facade construction reacts to fire. If the membrane is mechanically fixed and taped, there is the potential for the fire to spread on both surfaces of the material, as oxygen can feed into the fire on either side. This additional oxygen supply can also allow the fire to develop more rapidly. With a fully adhered membrane, only the outer surface can contribute to the development of the fire, as there are no gaps between the membrane and the substrate. This inhibits the supply of oxygen to the fire and slows down the spread of fire across the membrane. So, we've looked at how the wrap-tight membrane reacts to fire and how it complies with the relevant technical standards. But if we want to go beyond fire resistance and introduce a degree of fire protection, then another option is to use the fire shield membrane. Fire shield is a vapour permeable membrane with a unique surface composition which actively reacts to prevent fire taking hold. Fire shield can be used over insulation boards to provide an additional layer of fire protection to the internal structure of the building. In this comparative test, based on the EN 13823 single burning item test, the fire shield on the left reacts substantially less than the other Class B fire resisting membrane on the right. The surface of the fire shield acts similarly to an intumescent coating frothing up to protect the insulation boards and structure. In this test, the unique coating protects the sheathing long enough for the external fuel source to be exhausted and the fire to self-extinguish. The standard Class B membrane, although it shrinks away and does not contribute to the development of the fire, does nothing to protect the structure or delay the progression of the fire. Used in this way, fire shield can help prevent fire from outside the building causing damage both during construction and in service. During the construction process, a fire shield can also be used on the external cavity face to improve the fire robustness of closed panel assemblies when installed to the external sheathing alongside suitable non-combustible internal linings. Fire shield is the first fire-resistant vapour-permeable membrane approved for inclusion in the Structural Timber Association tested product listing for fire robustness during construction. As part of such a construction, fire shield will be part of a system to limit the spread of fire, which can allow for reduced spacing to adjacent properties. The Proctor Group's advanced construction membranes are supported by a range of technical services to assist in integrating our systems into whatever construction methods and practices are in use by our diverse range of customers. Perhaps the most important aspect of this is providing hands-on assistance with detailing of membranes and the production of drawings to allow correct installations to take place. Alongside this, we can also undertake WUFI assessments to ensure the specified construction is able to deal with the moisture loads placed on it, and to optimise the material specification to ensure the most efficient envelope is achieved. We also provide a full library of BIM data and template constructions for all our products, available in both Revit and IFC formats for compatibility with a wide range of software and systems. Finally, our on-site Toolbox Talks ensure the entire project team is confident working with our materials and has a full understanding of how they work and the benefits they bring to the project. That concludes our webinar today, so we'll now move on to the question and answer session. Please feel free to type questions into the comments box or email them to webinar@proctorgroup.com.
Good afternoon, everyone. My name is Ciara Proctor and I'm the Managing Director here at the A Proctor Group in Blairgowrie in Scotland. First of all, I'd like to thank everyone who joined our webinar. I hope you find it informative and enjoyable. I'd also like to thank Glynis Ritchie, who's our project coordinator, also based here in Blairgowrie, who's done a great job of explaining, the overview of airtightness in modular and off-site construction. At the end of the question and answer session, there will be a link emailed to you. This will be a link to the webinar itself, and feel free to circulate that to colleagues or others who you might find who may find it of benefit. There'll also be a link to a short survey. If you have time, please fill it out. It does help us understand and understand the good points of the webinar, where we could improve, and also topics for our next seminar. So we're trying to increase the number that we do, and we really want to make sure that they're informative and of benefit to those who are kind of plugging in and listening to them. I will introduce Adam Taylor, who is our Business Development Manager for the Building Envelope.
Good afternoon, Ciara.
We've got a number of questions that have come through on the chat during the webinar, which is fantastic, and a couple that we received via email before. So I will just kick off, and Adam will be answering the questions for us. The first one is from Michael Jones. In modular applications, there will typically be less issues with construction moisture. Is a WUFI analysis still advantageous?
For me, certainly, WUFI analysis looks further at the location of where the modules may be finished and positioned within the country. So we find that WUFI looks at localised areas rather than the UK in general. Furthermore, on from that, depending on when the modular is completed or how far it is completed, so i.e. is the external skin on, or is that being completed on site, it can then look at temporary moisture within products during that movement or during the application still being done on site.
Okay, great. Tom Fisher asked, how easy is it to interface externally instead of the traditional internal methods?
It's a really good question, because that's one we really put focus on introducing the Airtight into the market. The interfaces that we see in modular is ideally when the panels are being positioned together, and what we've done is introduce different materials to allow us to make that application simplified. So realistically, your joints from an external skin of making a building watertight, weathertight and airtight is around windows and the modules itself. When you look at trying to address airtightness internally, you do end up with a lot more service voids and penetrations from services going through the application. So theoretically, you're probably down to 2 or 3 interfaces externally over probably 6 or 7 interfaces internally.
Okay, good, thanks. Just another quick one from Michael as a follow-up to his last question. Is WUFI analysis beneficial in modelling the effects of damaged or incorrect vapour control or business services / ventilation?
Yes, it's always a difficult one to look at sort of penetrations and damage of incorrect vapour control layer. The way of using WUFI analysis is to actually look at the dimensions of how the building changes when you actually include a vapour control layer or remove a vapour control layer. That's one of the parameters that we look at right at the initial stages of design. And what we find in many applications is the exclusion of a vapour control layer sometimes allows the skin of the building to breathe easier. So it's almost like taking a waterproof coat and making it into a Gore-Tex breathable jacket. So you're actually improving the health of the building, and that can be looked at in depth within WFI analysis.
Okay, great. Duncan McAllister has asked, what kind of finish can you apply on top of the Raptite? Is it suitable, for example, brick and rain screen cladding?
Yes, again, when we look at the anything that sort of goes onto the external skin following from Raptite, there is normally some kind of bracketry system or kind of tie system. The unique components within the Raptite product itself allows the product to almost self-seal at these kind of areas. So what happens from that is basically any kind of rain screen bracketry system that's positioned or ties, it still allows it to be an airtight construction. So yes, we see materials like rain screen, brick slip systems and traditional brick used in the methods when we're looking at off-site construction.
Okay, good. Mark Dawson has asked if you would recommend air testing modules at different stages of the build.
It's a good one to raise, because if you can, it is ideal. What we normally see is the external of the skin being completed initially before we start any internal phases of construction. What this allows you to do is look at the envelope of the building to see whether it's airtight before you need to introduce anything internally. So before you start any plastering or plasterboarding and treating internally, you can actually look at how well the external skin has been sealed. So yes, it's definitely worth, if the parameters allow you to air test throughout the construction.
Okay, we have a question on fire shield here, but we have two or three via email, and 2 are related to Raptite, so I'll keep going with that and then we'll come on to the fire shield. Yeah. And again, if anyone has any other questions, feel free to put them in the chat box before we finish. So the 2 related to Raptite, can Raptite be used over a pitched warm roof?
Yeah, and again, what we see from modular construction is how the units come together is the roofing unit would normally come on separately against the other units. So by wrapping that itself on its own and then allowing it to be added to the modules, you're increasing the airtightness of the whole construction, allowing that warm space to be used significantly and still the airtightness to be achieved well.
Okay, and from the same individual, are there many ancillary products to be used when applying Raptite?
Well, one of the things that we've managed to do over the last few years of introducing Raptite into the market is our hands-on approach with detailing and working on compliance checks and install training with people in the modular market, in the offsite and traditional market. This has allowed us to develop in-house our own system products to go with that. So we have things like integrated corners that can be used within the frame of the construction, around windows, around doors. We have split liner tapes, which allow tapes to be used as applied on one panel and left loose to then be applied to the secondary panel as it's applied. And things like liquid flashing, which is a liquid material that breathes. So all of these ancillaries are part of the Raptite system and can be found online under the Raptite Ancillaries program.
Okay. We have a question from Andrew, again via email. We're getting more and more projects where we're not required to do contract administration. Are there installation methods we can specify that would be less open to abuse and survive without our regular inspections?
This is something that we've worked on considerably, and between our technical department and sales department, again, looking at how we look at compliance, install training, and actually detailing of the projects before they start. So one thing we would do is we would take some of the junctions and detail all that. We would then work with the install team on site or in the factory to train them to look at installing it correctly. What this allows for is installation methods to be improved. We also do an installation document that shows all these kind of junctions and images and photos of these areas. This means that yes, potentially you can use less regular inspections, knowing that the training has been taken out. And as a manufacturer of product, we like to look at compliance checks ourselves as well.
Okay, and again, just on the Raptite strain, another questions come through from Peter O'Donnell. How does the membrane handle nail penetrations from holding down straps, etc.? Is there additional tape sealing required around the penetrations?
Again, the product self-seals itself. We'd look at what kind of nails was being used, what kind of straps, when these are removed. We can either treat that with the liquid flashing over it, or we could patch it potentially. What we do is take the actual products that you're using and bring that in-house to do some inspection on that to see what kind of leakage you're getting from it. We're also looking at what kind of airtightness that you're requiring, and then we can make judgment from there whether there's additional things that need to be done to those areas.
Okay, good. And just coming back to the question further up the chain from James McGregor, how does Fire Shield work on decreasing its fire spread? Does this process cause the product to give off smoke?
It's a really good question, because there's a lot around classification of fire and membranes, and obviously smoke and droplets, etc. Fire Shield is actually a Class B product. It is S1, which is smoke 1, and droplet 0. So no, it doesn't give off very much smoke at all. And basically the way the product works, it's got a carbon impregnated face. So that what happens is the carbon then cuts out the oxygen from basically the air, which then allows for the material to slow the spread of flame across it. So it almost bubbles out and cuts out oxygen, which allows for a less standard of spread of flame coming across it. And that's one of the key products that we've really done to allow for that steady reduction in fire spread, if you like. So there's very little smoke, and the product works from carbon impregnation.
Okay, we've just had another one in via email which someone has brought through and highlighted to me. We'll try and answer it right now. It's quite a long one, but I'll read it out because it has come through. I don't understand how just an external airtight barrier is permissible. This effectively means that the WUFI calculations highlighted earlier are incorrect, as the internal layer is not airtight. This will permit movement of air into the insulation layer and thermal bypass. This movement of air carries moisture. By having the external air barrier creates a location for condensation to occur. All constructions need to have both an internal airtight barrier and external wind barrier, which is where RapTight works well. I say this is a building physicist and member of BSI Standards Group. I'd be happy to discuss, etc. So, Adam, is that something you want to address now?
Certainly, it's something that we've looked at over the many years with the likes of BOPAS and CWCT and many facade engineers, etc. Thermal bypass as an insulation layer is, yes, you can end up with movement of condensation through air, but thermal bypass needs to be theoretically treated in a different way to air tightness. So it would be quite a lengthy conversation to go into now, but certainly, Alex, I can follow up with you at a later stage. Thank you very much for the question.
Okay. I do think that's us come to the end of any questions, which is good, and some challenging ones there, which, as a business we welcome. So please feel free to ask away. We've got a lot of experience and a lot of expertise here, and obviously our main strain of business at the Proctor Group is heat, air and moisture movement, and the membranes that go with that, and the solutions and all the technical backup that goes with that. So we're very happy to have these conversations. I'd like to thank everyone for coming and ask Adam if you have any final thoughts.
No, like Kira says, we really appreciate any questions that you can give us, especially around the parameters of what we're looking at and how these products work well. We've certainly ventured into this market and seen very successful rates within what we're doing. So please do drop us a line as and when you can, and we can address these further. Thank you very much for your time.
Thank you. Fantastic. So you will, as I said earlier, you will all receive an email with a link to the survey and a link to the webinar, which you can circulate. And we hope you have a lovely remainder of your Wednesday. Thank you.